Everyone. We had a kind of intro yesterday, big picture kind of thing, and we finished off with a calculator and how you use a calculator to do sigma notation, and it kind of fell apart. It actually was correct what I typed. The problem is the calculator has limitations on computation, and 1,000 was too big. So if you make it 100 or 200, it's fine. So you're not going to typically have to do it for such large numbers anyway, so it won't be really a bit of a problem. So I have the video of yesterday's Zoom meeting, and I cut out the one where it didn't work, and I've appended one that does, so that you'll be able to see it. I'll also put a separate video of the buttons that you press to make Sigma work on Canvas. So it won't be in your Zoom lesson. It will be in your Zoom lesson, but just that little 5-minute thing where it goes through the stages and what buttons you press to make Sigma work on a separate video. And you'll find that in Canvas under the lessons, right? So the places where I put YouTube lessons and PDFs and notes and so on. So that's one of those things. So I think what I'm going to do right now is we're going to start at that kind of point, and let's look at using our calculator to do sigma notation. So suppose I need to do sigma n equals 1 to 100 n squared plus n. Now that's pretty much what we tried to do last time. Except I had 1,000, and 1,000 was just too much for it. So I'm now going to zoom over here, hopefully. And here we go. So it's on. Second list, math option 5, which gets you the sum. Then you go second list again. You go option 5 gets you sequence. In this case, it's going to be n squared, so n squared plus n, a comma, and then you finish with n, comma, 1, comma, 100, and a couple of brackets. And that's basically what it would look like on the calculator. And you hit enter, and see, it works. So we now have that feature, hopefully somewhere where you can, this time it's at the start of the video, so you can see that. What I'm going to do here is just go through some notes I've actually got on Canvas, so you can actually look at these notes, so you don't need to write anything down. I'll just talk through them. Here's some examples of some sigma. The counting variable here is I, but it could be any letter in the alphabet you like. This one is adding up I squared from 1 to 5. This is doing it from 3 to 7. And this is doing it from 1 to n. This one, you can't really write them down because n could be any finishing value you like. Here are some properties that work for sigma. Do you know if you just add up the same number, let's call it c, and you add it up n times, the answer is nc. If you've got a fixed multiple of something we're calling AI, then you can pull out the multiple from that and get this. If you do a sum, you can separate it into 2 separate sigmas. And if you go a difference, you can separate them into 2 separate sigmas. It's not true that a product can be separated. That doesn't. Okay, now let's look at a couple more examples of using sigma, and then we'll go and look at estimating the area under a curve. So let's suppose I do n equals 1 to 50, and it's going to be a half. It's going to be n squared, take away n cubed, and you square it. Now, if I was going to do this using the calculator, I would do the sum, I'd do the sequence, and then I'd do all of this guy. Now, it's half, you can actually do a half. It's a bit clunky if you want. You do a bracket 1 divided by 2 close bracket. If it's something that's pretty obvious, it's probably a lot easier just to call it 0.5, right? For calculations, sometimes you do that. Then you do a bracket, and then it's pretty much what you see is what you get. So this bit here matches this guy here. And then the last bit is pretty much obvious. So if you wanted to do this sigma, can you see that's what it would look like? Great. Now I am going to try that filler on the calculator, and we'll see how it works. Right, you should just be seeing the calculator right now, is that correct? Nothing else?
Yes. Yes.
But I'll clear this one out, and the first guy, option 5, gets you the sum. The second one, option 5, gets you the sequence, and then it's going to be 0.5 times a bracket. There's n squared, take away n to the power of 3, which is n cubed, close that brackets, and square everything essentially. Then you go comma n, comma 1, comma 50. You finish with a couple of brackets. And fingers crossed. Yes. Now, do you notice that this answer is kind of weird looking? It's 5.7 and then it's gone E10 after it. What's the calculator resorting to when it writes numbers in that weird way?
Scientific notation.
Yeah, exactly. So roughly, very roughly, this would be 5.7 times 10 to the 10. So that's a pretty big number, as you can imagine. Now what I'm going to do is look at the homework, and I'm going to see if I can find an example of sigma question, and then we'll do that as a kind of, showing you how you would do it in calculator. Okay, I've got one. This is my version of question 6. So let's see if you can see it. I think it's here. Right. One of the things that WebAssign does is it randomizes the question. So this is my question 6, but your homework question 6 might have, that 9 might be a 20 or something, right? So there will be differences. So anyway, this one here says k equals 1 to 9, 2 to the power of k minus 1. Now, the correct answer is 511, which is good, and that's what you would type in that box. So I'm going to look at this fella here and put them into the calculator, and we'll see if sigma comes up with 511, right? That's what it should. So clear this one out. Do the list guy, math number 5. The list guy, options number 5. The formula is 2 to the power of k minus 1. So 2 to the power of, you're going to have to put a little bracket around it. The k's or whatever letter just get turned into n's on our calculator. So that's essentially 2 to the power of k minus 1. I've just converted it to n minus 1. Comma n, comma 1, comma 9. Close think I only need 2, don't I? Yeah. Close with the brackets and enter. And guess what? It's 511. Let's look at that same puzzle if you just didn't do it using the calculator. Same question. Right, that guy. Well, if I wasn't going to do it with the calculator, wouldn't I have to plug k equals 1, which would be 2 to the 0, and then you plug in 2, then you plug in 3, then you plug in, I'm getting tired of this, then you plug in the last one. Can you imagine how much work you would have to do if you were doing it just by hand? Wouldn't you have to add up 2 to the 0 plus 2 to the 1 plus 2 to 2, blah, 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 plus 2 to the 7 plus 2 to the 8, enter. Now, how many places along that trail are you likely to forget something? Can you imagine that there's a lot of opportunities to screw that up, isn't there? Plus, it's just boring. I mean, how much typing do you really want to do in your calculator? So I am trying to sell Sigma to you, right? That it, using the calculator to do Sigma is a better way than physically having to do it by hand. Can you do it by hand? Sure. I mean, if it was a test question and your brain just totally forgot how to do the calculator version of Sigma, it would work, and that's fine. Do it. That's pretty much all I want to do with questions involving using the calculator to do Sigma calculations. Is there anything that you want me to go over in that? Or can we call that good? We're good. Okay, thumbs up is good. So, well, that's a little note to me. I will be doing later question 4 on areas and distances. So keep that handy. Before we do that, we are now going to estimate the area under a curve. And we're going to use left and right endpoints. And the first way I'm going to do it is with the numerical calculations. No Sigma. And then we're going to show you how to do it, numerical calculations, using Sigma. Now, some questions, the way the information is given to you, you have to do the numerical calculation without Sigma, because it's just not possible to do the calculator Sigma notation thing, right? The data isn't in that form. So the kind of questions that you're going to have to use number 1 in are going to be those questions where you are just given a diagram and your job is to estimate by reading off values. The second situation where you're going to do number 1 is when the information is just a table, with numbers in it. In those two situations, you will have to do number 1. In questions that have Sigma, then you can do them as long as they tell you a function. So if they tell you that the curve has the formula y equals x squared, or v of t equals t cubed, if it's written this way, you can use Sigma. So we're going to start by looking at those questions where you have to do them numerically, or at least I've decided to choose to do them numerically. And then we'll look at how to do them using sigma notation. So let's do number 1, numerical calculations. No sigma. Right, imagine that we have a function. I'm actually going to choose a function that has a formula, but I'm still not going to use the sigma notation. So suppose I want to do the area under the curve y equals x cubed, and I want to do it starting at x equals 1, and I want to finish at x equals, say, 2. And I'm being asked to estimate the area under this curve, and they will tell you how many strips. So let's say they want us to find this using n equals 4 strips. So far, so good, right? So first thing you do, you find a guy called delta x is basically the width of one strip. There is a formula for calculating delta x. It's b take away a divided by n. So who's this a and the b? A is the number, the value of x where you start, and b is obviously where you finish. So in this case, it's 2 take away 1 divided by 4, and that comes out to be a half, which is more convenient as a decimal. So that's step 1. You find that. Step 2, find, fancy word, find the ordinates.
Wait, how did you get a half?
Because I can't count. Did you all catch that deliberate mistake? Find the ordinates now. What do the ordinates mean? Do you know that if you're going to split this thing into 4 strips, then the x coordinate of where these vertical lines are called the ordinates. And they have a funny name, a funny labeling. The first guy is always called x0. This guy is called x1. This guy's called x2. This guy called x3. And the last one, in this case, is x4. So if you split your area into 20 strips, the first value, the a, will be called x0. And then x1, 2, 3, x19, and the last guy will be called x20. So that's what we mean by the ordinates. So in this case, x0 is 1. x1 is 1.25. Hopefully someone fixed that. Then it's 1.5. Then it's 1.75. And lastly, it's 2. I'm doing this pretty slowly, but are we comfortable that if I said from 5 to 20 and broke into 4 strips, that delta would be much bigger and the ordinates would be that? Now, there is a formula for calculating any of these ordinates. There is a formula for doing it. You do it by xk, so whatever k is 1, 2, 3, 4, 5, whatever you like, and it's a plus k times delta x. So let's see how that formula works. Suppose I wanted to find what x3 is, right? Just for example. Now, you know it's 1.75 because I told you it is, but let's see what it would look like. x3 would be a plus 3 delta x's. A is the starting number, 1, plus 3 lots of 0.25, and that gets you exactly what it should. Isn't it? Is we cool with that? Where do these come from? Now, step 3. Do the calculation. Now, if I am going to do a left 4 or a right 4, the calculations will be slightly different from each other, because in the left 4, every time you choose a strip, you choose the left-hand side to get the height. That's the left 4, right? So in this case, I could probably draw it in this picture. These are the rectangles that you would get if you were doing a left 4. Can you see that in each strip, I choose the left-hand side to decide the height of the rectangle, right? This would be a left 4. If I did a right 4, it would be somewhere up here, wouldn't it? It would be the right-hand side. So, doing the calculation, if you want to do L4, it's going to be delta x, f of x0, plus delta x, f of x1, plus delta x, f of x2, plus delta x, f of x3, which is just a fancy way of saying this. And all I'm doing here is pulling out the delta x. Well, what would that look like in this real example? Well, delta x is 0.25, and then it would be using that guy, that guy, that guy, and that guy. So what would that be? It'd be the value of the function at 1 plus the value of the function at 1.25 plus the value of the function at 1.5, and finally the value of the function at 1.75. So each one of these 0.25 times that would basically be giving you the area of the first rectangle, and this one here would be giving you the area of the last rectangle. All that I've done from this line to this line is that there's a little bit less work if you just pull out delta x, because they're all the same delta, right? They're all the same number, and it just reduces your workload. Now these fellas here are actually going to be calculated, right, using x cubed. So let's see what that fella looks like. It's going to be 0.25 times 1 cubed, 1.25 cubed, which is 1.953125. The next one is going to be 1.5 cubed, which is 3.375. And then the last one is going to be 1.75 cubed, and that's going to be 5.3 0.59375. So that's going to be 0.25 brackets. That, and that all added. Yikes. Okay, here goes. 1 plus 1.953125 plus 3.375 plus 5.359375. Hopefully I did all that correct. And I now have 11.6875. And nothing 0.25 then times 11.6875. And the answer I now have is 2.921875. You're almost guaranteed never to have that accuracy. The book or the homework will say, give your answer rounded to 2 decimal places. And if it did, the answer would be 2.92. And in that little box, that's all you would end up typing. Now, there's a lot of steps here. I don't suggest that you will always need to write them down, but I'm putting this one in as like a template so that you can see, I can't think of anything I've missed out here, right? But you might eventually say, look, I don't need to write this down and this down. I'll just go straight into that. And I won't write this down because this will happen in my calculator and hopefully reduce your workload a little bit. Now, if you want to get the other version, it's going to look very like this, but we're going to do R4. Then it's going to be delta X. Now, if you do R4, aren't you going to use X1 for your first rectangle? The height's going to be on the right-hand side. So this formula here is not quite the same. You start at 1, and you go and you do the second rectangle would be this guy. The third rectangle would be this guy. And the last rectangle would be that guy. Do you see in this case you use 0, 1, 2, and 3, and in this case you use 1, 2, 3, and 4. Now if you pull out delta X, you get this. Then that becomes this fella. F of 1.25, F of 1.5, F of 1.75, and you finish with F of 2. And that becomes 1.953125, 3.375. The third one is a 5.35935, and the last one is 8. So that becomes 0.25, and you add all these together. So I have 11.875, add an 8, take away. And I hope I got this right. I get 17.734375. which I can then multiply by 0.25, which gives me 4.43359375, which is definitely overkill. And this fella here is going to be 4.43. Now that is the worst version of this calculation. So let's look at some shortcuts, numerical shortcuts. First one, if you are being told in the question that it's to be to 2 decimal places, right? They only want the answer rounded off to 2 decimal places. You do not need to write this kind of accuracy. You do not do 2 decimal places, because if you round off all these to 2 decimal places, your final answer will be a little bit out. What you have to do is you round off to 3 decimal places. So that's the rule. If they want the answer to 3 decimal places, round off all your working to 4 and you'll be fine, right? If you want it to 2 decimal places, round off all your working, that's these guys here, round them off to 1 more decimal place, right? So if they only wanted 1 decimal place, wouldn't this guy just turn into 1.95? This guy would be 3.38. This guy would be 5.36, and that would still be it. So there's one way to reduce your workload. Look at the accuracy that they're asking for and adjust your working accordingly. The second one is kind of sneaky, but it works. Have you noticed that the difference between this answer and this answer is that this one uses a value at 1 and this one doesn't, and this uses the value of the function at 2 and this one doesn't? What does that mean? It means that I can use this answer here, add that guy, and take away that guy, and I'll get the answer. Does that make sense? You're using the first 4 or you're using the last 4. So the difference is that they share a lot of the working, don't they? They share all the numbers in the middle. The only difference is that this one uses an extra 8, but doesn't use the first number. And hopefully that works. Of course, the best way to do this entire calculation would be to do it in sigma. So that's how you could do this numerically without using sigma. The next one I'm going to show you is how to do it numerically, but when the information is given to you in a table. So suppose that you are told at certain times what the velocity of a moving object is. So at the beginning, at the 1 second mark, at the 2 second mark, at the 3 second mark, at the 4 second mark, say at the 5 second mark, that one there. And I'll just put in random numbers, 5, 7, 8, 7, 9, right? So at the 2 second mark, this thing was moving at 8 meters a second. At the 5 second mark, it was moving at 11 meters per second. And we're being asked to find what the area under this curve would be. Actually, what they'll say is estimate the total distance traveled, which happens to be the area under this curve. So how's this one going to alter what we do? Well, we add a couple of things. We're going to be using 5 strips, which is pretty obvious. This guy here is going to be called T0, T1, T2, T3, T4, T5. You should actually be able to tell what delta T is by looking at the table. But if you did 5 take away 0 divide by 5, you'd get it. But can you see in this case, the table goes up in 1 second units, doesn't it? Can you imagine a table that went 0, 0.1, 0.2, 0.3, 0.4, 0.5, then wouldn't delta t be 0.1? Right. Now, let's just do one of the two. Let's suppose I'm going to use as my estimate L5. Now, when you use L5, it's delta t. Which guys do you use when you're doing an L5? Do you use those 5 guys? Or do you use those 5 guys? Because that's the only choice. If you do L5, is it that set of numbers there that we're going to use?
Yes.
Right? Now, why do I know that? Well, you notice if you have these guys, isn't that the first number? That would be the one on the left. So left always uses the left side of the table. Right always uses the right side of the table. You don't use all the numbers because the way it works is that one of them doesn't get used. So in this case here, we would be, I'll cover this up, we would be using those left numbers. So I can basically just say that guy, add that guy, add that guy, add that guy, add 9. Oh, and since delta x is 1, won't that be 1 times these? And that comes out to be 12, 20, 36. And do you see when it's a table that it's a lot less work? Because most of the information's kind of constructed for you, right? It's just there to be read off. The width of the rectangle is going to be the difference between 2 consecutive numbers, right? And the height of the rectangle is going to be the value at that point. So it's basically these numbers here. Actually, I said I wouldn't, but I think I will do it. What's R5 going to be? Well, it's going to be delta t, but the right-hand side. And the numbers here are 7, 8, 7, 9, and 11. Now, those numbers are very easy to do in my head. So 15, 22, 32, 42. But I could if I wanted to. Isn't the difference between these and these that you add an 11 and you take away a 5? So if you take this answer, if you add 11 to it and subtract the 5, you should get it, right? So if you add an 11 and subtract a 5, isn't that basically an extra 6? Now, that might be worth it if it's a really big, long table. Can you imagine it's a table with 50 numbers in it or something ridiculous? The first time you got to do it, but isn't the second time you just need to add 1 number and take away 1 number and you're done. And that reduces your workload again. We're all trying to find shortcuts to reducing our workload. Now, in this particular example, don't the numbers go up and then down and up again, right? That means that I can't say that that's an underestimate or that's an overestimate. All I can say is that they're my estimates, right? In this early question, isn't the function increasing? So the 2 answers that I got, if I can find them now. There we go. Won't that be an underestimate? And won't that be an underestimate and won't that be an overestimate?
Yeah.
Sometimes you're asked, you know, which one's an under and which one's an over. That only works if the function is always increasing or always decreasing. If a function just goes up and down like a yo-yo, you can't say anything along those lines. Are we comfortable so far with numerical with a table? Numerical with a function?
There is one question in the chat.
Yep.
I don't know if you can see it from your screen.
I can't really, but I'm glad that you did that. What does the question?
So Ian was asking, can we only use sigma when delta t is going to be an integer, unlike the previous question where delta t was a fraction?
You can use delta t as a fraction. I'll pretend look. Yeah.
Sorry, you're going to show that in the next couple slides. That's why I didn't want to like ask over.
No,
audio.
no, I
Okay.
wasn't actually, so it's a good question. Can you imagine that the table was these numbers? Won't delta t be 0.5?
Yeah.
So yes, you could, in a table format, delta t could quite easily be a fraction, in this case 0.5.
Okay, and then is there, I'm assuming there's a way to set that, just basing it off of what Matthew said in chat.
There would be a way to, I didn't catch the rest of what you said.
Matt said that there's a way to set delta t in your calculator. I just didn't know whether I missed it or not.
There's like on
Well,
the menu.
there
it says,
is, yes.
on the
You
menu
know, when
it
you're doing this function up here, there is a way you can do that in your calculator.
Okay.
What that'll do, it'll turn into a table, so you can basically use this technique.
Okay.
So you could take a function, make it a table, and then use this technique.
All right, thank you.
Right, sigma does that even better than a table, but that's just my opinion. Right, so I'm going to have to show you the next one, and do we got 4? No, okay. I'm going to go to question 4 from the homework, and I'll see if we've covered that yet. If not, then I'll start covering it right away. So let's see, question 4. Where are you? Where are you? Here you are. Okay, so. Okay, this is, I believe, this is question 4. Person asked, is this the one you're talking about?
Yep.
Yes. And it goes into a whole load of stuff with deltas and n's. Yes. Nope, I will not be covering that today. That's pretty much the last part of what we'll cover. That is the generic version of how to find the exact value for the area under a curve. It's the equivalent of, in Calc 1, the limit as h tends to 0 kind of stuff. Remember doing that weird and wonderful thing to get the exact slope of the tangent line? This thing that you're seeing with all those 8 over n's and sigmas, and, well, doesn't use sigmas, but it really should. That's where that's going to come from. So you're just going to have to leave question 4 for another day, but I will get to it. So what am I going to do for the last 6 minutes? I think I will show you how to do an estimate from a graph version instead. Yeah. I couldn't go through what you would need to do that question in 6 minutes. There's a lot more to it than that. That's why I'm kind of postponing it until we reach a better place. Right. This one is not going to work well, but it's the best I can do. Imagine that you're given a function, and it looks like that. And it's going to go 5, 10, 15, 20, 25, 30. I don't need to go any further. And let's suppose that it starts at 0 and it finishes at 1, 2, 3, 4, 5. And it finishes at 5. And we're being asked to find this area under the curve. But there is no formula. They just give you a picture. And they tell you that it's going to have 5 strips. And let's find L5. Now, if you're going to do L5, it's going to be delta x, the value of the function at x0, the value of the function at x1, x2, I'm running short of room here, aren't I? x3, I'll just move over here, x4. That's the general version of every L5 in the world, right? Now, that's A, that's B. Won't delta X be B take away A divided by N? And I've made my life easy. I've made delta X 1, which you could probably guess just by looking at the table, right? Or the graph. Now for each one of these fellas, there would be a strip. This fella is X0, this guy is X1, this guy's X2, this guy's X3, this guy's X4, and the last one is X5. So in this case, I'm going to be looking at the value of the function. Oh, am I going to start at 0 or at 1? Which will be the first X value to use if I'm doing a left? 0 or 1? Yes, Noah?
Should be the 0.
Yes, it is. So we're going to find the value of the function at 0, at 1, at 2, and at 3, right? And this is where the problem starts. There isn't a table where I've got numbers to use. There isn't a formula that I can plug in and get the y value. There's just a graph, which means you're going to have to estimate or guesstimate the answer. Right, the value of the function at 0, I'm pretty sure is 10. The value of the function at 1 is probably, and that's just probably, 19. And the value of the function at 2, I'm going to call that 20. Oops, I forgot my F4. The value of the function at 3 is, I don't know, 22. And the value of the function at 4 is about 23. Now, there's a lot of wiggle room in quite a few of these. I say 21, you might look at it and say 22, right? You cannot do these questions to 4 decimal places, right? Nobody in their right mind would expect you from a pretty primitive diagram to get anything remotely accurate. So you do the best you can, depends on the context here, it's whole numbers. And now I can do 45, 65, 75, 85, 94. So that would be my answer to the area under this curve. I would say it was 94. See if I can squeeze R5 in. R5 will start at 1 and finish at 5. That's 1 times the value of the function at 1. So what's that? 19, add 20, add 22, add 23, and the last one, I'm going to call it 25. And that's going to be 1 times 39, 49, 59, 61, 71, 81, 84, 104, 109. And that's going to be 109. In this particular picture, are either one of these an underestimate?
Yes.
Yeah, obviously the small one, right? That makes this the overestimate. Doesn't that then mean that we are sure that the real answer is somewhere between the over and the under, right? The reason you can do that is, isn't this function always increasing? Sometimes it's not increasing very much, but isn't it always going uphill? If it's always increasing or always decreasing, then the little guy will be an underestimate and the big guy will be an overestimate, and you can guarantee that. So if you see a table of values and all the numbers are getting bigger as you read along, or all the numbers are getting smaller as you read along, then those two left and right are over and underestimates. And that's a good thing to know, because it actually tells you a little bit more, doesn't it? If you can say the right answer is between these two. Now, before we go, will you all make sure that you say hi? Because we're taking attendance now. So you go to your little thing and you say bye-bye or hi or whatever, and we'll be finished. I'm counting. There's only 10, 11, 12, 13, 14, 13. Come on, there must be more of you. There we're going. Almost done. 17. Anybody else? That means there were 17 here today then. Hopefully you all caught that message. Okay, so what's going to happen tomorrow is I'm going to show you how to do areas under curves using Sigma. And those are only going to be useful, that technique's only going to be useful when you're actually told what the function is. So they tell you this guy is y equals x cubed or something, right? But for those questions, it's a lot less hassle than all this stuff, right? A lot less hassle. So hopefully I'll convince you. A bit ugly, but it's doable. Oh, looks like we may have got one more person, 90. And depending how quickly that goes, because it's hard to predict, the last thing I'll be able to show you is how to do question 4, the generic perfect answer for the area under the curve, that horrible thing that you saw about 10 minutes ago. And that will be us finished 5-1. 5-2, strangely enough, is really just finding areas under the curves, but using some more techniques. Midpoint, trapezium, Simpson. And thankfully, once all that's done, we can say bye-bye to boring numerical, and we can actually start doing cool math with algebra and x cubes and stuff. And you'll be able to find how to find the area under the curves very quickly and very precisely. Just go. But that's us for today. Bye-bye, guys.